Alright, so let's go over worksheet number 4. So number 1 asks, what is the correct chemical formula for ammonium perchlorate? So ammonium over here is just NH4 plus, and perchlorate is ClO4 minus. So ammonium's got a +1 charge, and then the perchlorate's got a -1 charge. So when we put these together, in order for us to make a neutral molecule, we got to put them together in a 1-to-1 mole ratio. So it would look like this: NH4, ClO4, just like that. And this is ammonium perchlorate. So the correct answer is B. So for number 2, what is the charge on copper in CuNO3 2? So to start off, NO3 minus, so NO3 has a -1 charge, is called a nitrate. So we're trying to find the charge on the copper here. So we have 2 of these, so 2 nitrates, with each nitrate having a -1 charge, means that the overall negative charge on the molecule is a -2. So that means that in order to make the overall charge 0, the copper must have a +2 charge. Okay? So in other words, this is like saying copper 2, we've seen this before, copper 2 nitrate. Okay, so the correct answer for 2 is also B. So number 3 says, why does electronegativity increase across a period and decrease down a group? Well, we can refer to a periodic table here and see that the electronegativity tends to go upwards, so it increases as you move from left to right along a period. It also tends to increase as you go up a group. So the overall electronegativity trend across the entire periodic table is that as you move from the bottom left-hand corner to the top right-hand corner, your electronegativity is going to increase. Okay, so the correct answer for number 3 is C, increased number of protons going left to right across the period. Well, absolutely, that is absolutely one reason why the electronegativity increases. So we know that because as we move from left to right along the periodic table, our atomic number increases. And the atomic number expresses the number of protons there are in our elements. And then the other reason suggested in C is that increased electron shielding occurs as you move down a group. So what exactly is electron shielding? Well, as you move down a group, what you also see is that the atomic radius increases. So it's the size of the atom. It gets larger as you move down a group on the periodic table. So for small atoms, what you see is that the distance between an electron, an outer electron, and the nucleus is really close. So these two particles, so you got the positively charged nucleus and then you got the negatively charged electron, are going to be really strongly attracted to each other. But in a large atom, though, you might have an electron that's out here in the valence shell, and it's really far away from the nucleus. So, okay, so there's an electron, and it's really far away from the nucleus. It's not going to feel as much of the attraction to the nucleus because it's shielded away from the nucleus by these electrons that are closer to the nucleus. So this electron is going to feel a lesser attraction to that nucleus. So I would say that the larger atoms experience more shielding. So what we can follow up with is that larger atoms have smaller electronegativities, and smaller atoms have larger electronegativities. Because if you were to get an electron somewhere nearby, it's going to really pull into it because there's going to be a substantial attraction between an electron and the very nearby protons in the nucleus. That's not going to happen if you have an atom where that nucleus is shielded by inner core electrons. So just remember, the larger the atom, the smaller your electronegativity. Okay, so the correct answer for 3 is C. Number 4 asks, which of the following would you expect to have nonpolar covalent bonds? Well, the question here is, how do you know if it's a polar bond or a nonpolar bond? What we can do is something very simple, and we can use electronegativities to tell us about whether a bond is polar or nonpolar. So suppose we have two atoms here, A and B, bonded together by some kind of a bond. And we want to learn about the polarity of that bond. How polar is that bond? What we can do is we can look up the electronegativity values of A and B and just take their difference, subtract one from the other. So it would look just like this. So our change in electronegativity, or the difference in electronegativity, is going to be the electronegativity of B minus the electronegativity of A. You go, okay, well, how is that informative? What we can do now is we can construct a scale that looks something like this. If your electronegativity difference here, your delta chi, is between 0 and 0.5, this would be considered a non-polar bond. If your electronegativity difference is between 0.5 and 2.0, then this would make a polar bond. And over here, if you go all the way up past 2, these are called ionic bonds. So basically, the electronegativity difference between A and B is so great that one of them is ripping an electron off of the other. And we're very familiar with what kinds of scenarios make up ionic bonds. Those are scenarios where we have metals and nonmetals. So we got now a whole scale here. We go from nonpolar bonding to polar bonding to ionic bonding. And now we can use this to solve number 4. So in number 4, we have carbon, hydrogen, 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 hydrogen. This is methane. And what we can do for methane is we can look at the electronegativity difference between carbon and hydrogen. And what we find is that, so we look up the electronegativity of carbon, and we look up the electronegativity of hydrogen, and what we get is, for carbon, it's 2.50 minus 2.20 for hydrogen, and what we get is 0.3. That's our electronegativity difference. That falls right in here in between 0 and 0.5. So that tells me that the carbon-hydrogen bond is nonpolar. Okay. Let's see, what is B? B is sodium chloride. Oh, well, we don't need to do anything for sodium chloride because we know right off the bat we got a metal and a nonmetal, so that's going to be ionic. Clearly, that's not a covalent bond, so that's going to be wrong. Okay. And let's look at one more example. We got HF. So we know that this is a covalent bond, and we can probably guess as to whether it's a polar or nonpolar bond, but let's run through the electronegativities to actually find out what kind of a bond this is. So we can go back to our table, and we find that the electronegativity for fluorine is a whopping 4.17. And we subtract from that the electronegativity of the hydrogen, and we get 2.20, and the difference between those is 1.97. Oh, so close to an ionic bond. That is literally on the verge right there. of being an ionic bond. So what this would indicate is that this is a very strong polar bond. But it is a polar bond nonetheless. And you can do a similar analysis for carbon dioxide. So the correct answer here, of course, is going to be A, methane, because the carbon-hydrogen bonds are nonpolar. So for number 5, we can do a similar sort of analysis where we take a look at the electronegativity differences of the atoms in those molecules. You got BH3, you got aluminum oxide, you have phosphate, and then you have silicate. You can look at the electronegativity values of each of those elements and just evaluate for yourself where on this scale do the electronegativity differences lie. And what you'll find is that BH3 is nonpolar, and aluminum oxide is going to be ionic, and you can also use your intuition there because aluminum's a metal and oxygen is a nonmetal. And let's see here, we got phosphate. So phosphate, it definitely puts you right in here, right in this polar covalent bond area. So phosphate would be the correct answer. And silicate actually tends to be ionic. And so what we're going to find is that the silicate bonds are ionic bonds between silicon and oxygen. So the correct answer for number 5 is the PO4 3-. So this is the polar covalent example. So the correct answer is C. Let's take a look at number 6. So number 6 says, which of the following elements do not follow the octet rule? So oxygen, sulfur, boron, or nitrogen? Well, to not follow the octet rule, basically what we're saying is that we are allowing an expanded octet. What does it mean to have an expanded octet? This means that we are now capable of filling the d orbitals. And by being able to fill higher energy orbitals, and you got these spacious d orbitals, you are now allowing for more bonding. So sulfur and boron are very prominent exceptions to the octet rule because they participate in, well, for example, sulfur participates in this expanded octet. Sulfur allows for more bonding by filling the d orbitals. So by filling d orbitals, you're basically making more room for extra electrons to come in and bond. Boron is a little bit different. It does not really participate in an expanded octet in the same sense of making more room for bonding. Boron is one of those elements that's actually happy with fewer bonds. So it does not necessarily need to form a full octet in order to be happy, sort of speaking. So it's generally electron deficient, and you also find this in other elements from group 3A. So certainly sulfur and boron are not the only ones that do this. Phosphorus is another interesting example of the expanded octet, but the correct answer for number 6 is sulfur and boron. Speaking of phosphorus, we're now going to take a look at the phosphate ion in number 7. Now number 7 asks us to count the number of electrons in the phosphate ion. So PO4 3-. So it's PO4 3-. Well, when I count electrons in a molecule, I like to draw the structure. And since number 8 asks us to draw the structure, let's go ahead and throw number 8 in there as well. That way we can do both simultaneously. So first we have to identify which of these is going to be the central atom. And the central atom is going to be the phosphorus. And then we can surround the phosphorus with the 4 oxygens, just like that. And then we'll fill all the oxygens up with their lone pairs. I tend to prefer using dots. Some people like dashes. The important thing is just that you have the right number of them. Okay, there we go. There's a structure of phosphate. I would suggest a slight modification to this structure, however. Even though that's okay, I think we can improve it. And here's what I think we can consider. So remember how I mentioned in number 6 that phosphorus is one of those elements that can have an extended octet? So by that, what I basically mean is that phosphorus can have an extended or an expanded octet because it shifts one of its lone pairs from the 3s orbital into an empty 3d orbital. And in doing so, what it does is it allows electrons to fill the 3d orbital and give it the possibility of forming a 5th bond. So you can have up to 5 bonds here on that phosphorus. And that happens to be where it's the happiest. So let's go ahead and figure out how we can do that. Using these electrons, what we can do is choose any of them. We can say any lone pair. Let's go ahead and just take this one for convenience. We could have done any one of them. They're all the same. So I'm just going to take this lone pair right here and move it down into here. And by doing so, what I'm indicating is that now this lone pair of electrons is going to come down and participate in a covalent bond between the phosphorus and the oxygen. And since it's 2 electrons, we are establishing a covalent bond where 2 electrons are being shared by 2 atoms covalently. So all we're doing here is we're now modifying the structure to where now, instead of a single bond, we have a double bond between the phosphorus and the oxygen. And now that we've taken away 2 of the electrons here out of the 6, we're left with 4. So we've taken away, or you could just say we've taken away 1 of the lone pairs out of 3, so now we are left with 2 lone pairs on that oxygen, and all the other oxygens remain as they have been before. And let's remember our charge, just like that. So now this right here is the structure of phosphate. PO4 3-. Now we can count the electrons. So now we can see why I like to draw the structure first, because I can go like this now. I can just literally count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Are we done? No, we're not done. What we also need to include is the electrons that are participating in covalent bonding. So we got 22 lone pair electrons, and then we also got some of these. So let's count these. So we got 22, now 24, 26, 28, 30, 32. So there are a total of 32 electrons. So with 32 electrons, the correct answer is C. So number 9 says, if a molecule has a central atom connected to 4 other atoms and the central atom has a lone pair, what shape would you predict using the Vesper theory, or the Vesper model? So I came up with an example here, and first of all we have to identify where this, or which of those is going to be the central atom. And I think it's probably going to be the sulfur, so let's go ahead and put the sulfur there. And then what we can do is we can surround the sulfur with fluorine atoms. That seems pretty reasonable, so let's go ahead and do that. So we got fluorine here, fluorine there, there, and there. And the reason I drew it in this rather odd conformation is because I have to remember that I need room for a lone pair. And that lone pair I can put right up there. There's my lone pair. So, what kind of a geometry does that look like? This looks like a seesaw geometry. So remember, for a seesaw geometry, you need you need to have a central atom that is connected to 4 other atoms, and that central atom must also have a lone pair. So if you got those 2 things, your molecule is going to have seesaw geometry. So the correct answer then is D. Finally the last one, number 10. Number 10 says, using the Vesper model, what would you predict the shape of the phosphate to be? Well, that's an interesting question. So let's go back to the structure of the phosphate that we drew. So we had a double bond oxygen here. We'll go ahead and put all of our lone pairs in there. Just like this. And we have to remember that it's a 3- charge. And we have to ask 2 key questions. How many atoms are bonded to the phosphorus? There are 4 atoms bonded to the phosphorus. Okay, that's one key piece of information. The other key piece of information is how many lone pairs are on the phosphorus. There are 0 lone pairs. There are none at all. No lone pairs on the phosphorus. So what kind of geometry is characteristic of 4 atoms bonded to the phosphorus with no lone pairs? This is the tetrahedral geometry. So the correct answer for number 10 is B.